So I'm Suchakrapani Sharma, but you can just call me Suchakra. And this work is also having some work by Thomas Berto, who is a student. So I'll just get right to it because there's just too much to show. So I'm a PhD student in Polytechnique, Montreal with Michel, who's my supervisor. He's also here. I work on debugging, tracing, and aggregation, tools like aggregation, TPPA. The other student is Tama, who's not here, so I present some work on his behalf. He's a recent master's student, and he works on embedded systems, but now he's working on financial tech. So let's get to it. So the agenda today is latency. What's latency? It's going to be a little bit basic for everybody, but I'll just run through it. And what's hardware tracing, what it can do for finding these latencies, or what it can do generally for you. And then we go a level below that and just go to baremetal tracing, where even if we don't have an OS, how to get data from devices. So latency is actually this. You press a button, something complex happens, and you get something on the screen. So whatever happens in between is the latency. So just not to make it so simple, it's not actually that simple. There's a lot of stuff which is going on. So instead of just thinking about pressing a button, you can think of it like anything else going on. It can be network input coming in and your card getting the interrupt, and then the interrupt getting processed. So there can be a lot of stuff going on. So we cannot actually find out the moment you press the button. There's a lot of stuff which is going on. Electrons are flowing through the device. Okay, you cannot measure that latency. So we have to at least decide what's the first step. So we say that, okay, there is something which happened, and this is an interrupt which comes from the controller, and now it's coming to the CPU. Okay, and we say that that is our first instance from where the latency will probably start. Then the kernel receives the interrupt, and it's going to be handled. So usually on Linux, it's like a do RQ getting called. So we call it's the we say that it's a delay between the interrupt and the interrupt actually getting fired and the do RQ, the kernel receiving it. So then there can be latency of because of the interrupt handler. And that's when the interrupt handler is going to do its task, and it's going to ask a task to be scheduled. It may be a kernel thread which is doing, which is processing the interrupt. For example, if you have a network, so there can be a RQ thread running, and it's processing that interrupt. Or it can be the user space task which was waiting, and it's now going to be scheduled. So the request for scheduling of this task, for example, it can be a sched switch, and then a sched wake up. And the task actually getting scheduled would be the delay of scheduling. There are multiple other steps which happen in between that, but I'm just saying that that's the scheduling delay when a task has to be scheduled and it actually gets scheduled. And then the execution delay when the task is getting scheduled and the process has to come out of its syscall, which it may have given, and the task actually exists. And then the task is now in and then the processing now goes on to the user space. So we can think of the whole latency as this big distribution, and we can try to analyze what happens in between in each pass. There can be locking going on, there can be preemption going on. So we can analyze that. So there are a lot of challenges in measuring such latencies, because latencies can probably sometimes be non-deterministic. You don't know that it's going to repeat every time. It can be sporadic. We found that in our lab once while testing on ARM Jetson kit, and we found that after a week, we found there was an 8 millisecond delay, and before it was just constant 100 microseconds always for the scheduling. It was the wake-up latency, so it's sporadic. There's no way we could find out just in 5 minutes that we are going to have such kind of latencies. So we need some ways to do this kind of continuous monitoring. The techniques which are going to measure the latency itself, they would probably be in the critical path, so they will themselves add some kind of latency. So if your job is to just, if you want to not have that kind of latency, then you need better tools which allow you to do that. There are multiple SoCs, they have multiple processors, there can be heterogeneous systems. So how do you find latencies between all of these components? I mean, one task may be delegated to another processor and that may be causing some latency, so how would you measure that kind of stuff? We can use sampling techniques, but they are very limited viability. If you sample such kind of data, you might just lose the events for the actual latency which you wanted. So a tool which everybody has been using, and it's very cool. I actually learned everything about the links from just ftrace. It's really awesome. So some interesting events for our purpose may be these, which I found. Like you can put a filter on do IRQ, and you can just see when the do IRQ is happening. You can enable some events like sched waiting, sched wake up, sched switch, and then when you run your program, you would get a flow which would be like do IRQ, IRQ handler, sched waiting, wake up, sched switch, and then you can look at the timings for all of them. But it's a bit complex because it's not this constant flow which you're going to see. You have to analyze it manually to see what is being correlated with the previous one. Is the wake up related to the next switch? You have to look at the events yourself. So there are some stuff which has already been done in ftrace. There is RQs of and preempts RQs of trace target. So which measures, so RQs of actually measures the time at which the RQs were disabled. This is a very important event. When the RQs were disabled, then nothing can actually be run on the CPU, so you would want to find out that latency, that's like a true latency. So that kind of target is already there in ftrace. And the RQs of latency and the preempt of latency tracker looks at when the preemption was disabled, and there's preempts RQs of which looks at when either of it was disabled. So you can use that, and it will give you the latest maximum latency which has been encountered till now. So it keeps on overwriting whenever it gets whenever it gets a latency which is more than the previous one, it just overwrites it, and you see it. It even gives you a stack trace of what led to that latency. So there is wake up RT. It's good for using this to find scaling latencies, and it just works on the same thing as before. You can just enable it in ftrace, and you can find out wake up latencies. There are some other tools which are there. Matthew has already discussed, so I need not explain all of it about latency tracker. It's a really amazing stuff which they do. It's just like lot of analysis, and you just have a single module, and you could find wake up latency of CPU latency when the task was not on the CPU. Syscall latencies happening in between the syscalls, entry and exits, IO latency, and you can have views in ftrace or LTTNG. So it's not just only LTTNG which it's going to serve. You can have such views there. There is eBPF, which is targeted for just analyzing one shot of latency problems. If you're following Brandon, we recently posted a couple of examples of request latencies on. So it's just small scripts which can directly run in the kernel and just give you the output. But they're not meant for like long running purposes. There's latency talk for normal systems. It's not that useful for real time. So there is perf sched. So this I just recently found out, actually I did not know about that. So perf sched records all the scheduling latency, and it gives you a very nice big chart of, okay, these were all the K workers, RSU sched, or whatever threads were running, and the scheduling latencies they had. So it's also pretty nice. Then we have already had the latency tracker. So the questions arise: what happens before the kernel actually receives an interrupt? Is there a way to find out what happened before do IRQ? What was the exact flow which led to the do IRQ? So a good thing is, if we have the whole flow of the program, we would probably be able to analyze it ourselves. Does the tracer affect the test system itself? If you are trying to use the tracer, is it going to affect the system? Are there some regions in the kernel, or are there some regions in your own user space which you cannot trace, but you really want to trace them? Is there a way to do that? And can we observe the system without being in a critical path, like just from above, can we see what's going on? So the answer is that we need a precise instruction and data flow, which is coming directly from the processor. It may be overkill for a lot of cases, but it can be quite useful for if you want very dedicated analysis to be done. So we start with hardware tracing. What's hardware tracing? What's going on in this domain these days? So it's really cool how people had started doing all this crazy stuff back then. So it's an article from '98 where a guy actually has some action codes which he sets in his code, and when the action code gets fired, he saves the data to a logic analyzer, and he observes it on the logic analyzer. So that's like the first. I don't know if it's the first example, but it's one of the early examples how we're using hardware tracing to send data out directly from the processor to an external analysis unit where you have the whole instruction flow, and then you could make out the flow themselves. So these days it's been adopted in mainstream by ARM, by MIPS, and by Intel. And for example, ARM had embedded in circuit emulators for quite some time. They would just directly access the data bus, and they would just directly access the address bus and look at what's going on. And you needed to have external tools which you would collect, and then you could analyze your system through JTAG. These days, ARM is putting a lot of efforts in ATM and PTM, embedded trace macrocell, and program flow trace macrocell. And it's been now grouped into a big umbrella of course. If you attended Matthew Borges' talk yesterday, you would have some information about that. Intel also started early with the last branch recall support, and which was, they would just recall the last branch, we'll come back to that later. And the branch trace store, I'll explain them a bit later. And MIPS also has support in terms of PD trace. I have not tried this one. So what's hardware tracing? What's the typical arrangement? So that's what I came up with from analysis of different hardware traces, trace infrastructure in different processors. So there can be multiple CPUs. They all have trace modules. There's a dedicated trace bus, and some of them may not have it. The data would come on the trace bus. It may go to an on-chip buffer and be consumed directly by the software, or it can go to a transport layer, which can probably put the data to an external trace port, through which it goes to an external hardware, or it may go to the system's memory bus, and there's an in-memory buffer which is buffering the traces, and then you consume all of it in your software. And the software then decodes it, and you can completely see the trace. You can control the trace by putting a trace control. Asking the processor for all of this information is very expensive. So most of the times whenever the data is being sent, it's very highly compressed and highly encoded. And most of the research which had been happening was compressing the data and making the size small because it's too high. It's in megabits per second, seriously. And but these days, because the tech is improving so much, they are able to use some tricks, which I will tell. And they are now merging everything in perf slowly. ARM is doing that, and Intel has already done that. So they are merging all of the infrastructure together, so it can be utilized very easily by everyone. The decoding is performed offline. I've already told about that, and it can be just the instruction flow, or it can be the data flow. Because if you have data plus instruction both, it's a bit more expensive. So you can make things fine gradually. So as I've already said, architectures which are supporting its core site on ARM, processor trace on Intel, but Intel processor trace just does program flow, where ARM allows program as well as data flow, and then there's MIPS. So let's start with Intel processor trace, something which I've been interested in working on. So previously there was something called as last branch record. They would just save n number of branches. I think it was 7 or 14. It depends on the processor. And you could just save it in MSRs, and then you could say that okay, the branch trace messages were then sent on the system bus, and you could just see that okay, these were the last 10 branches which we did. But it's good. It was very cheap, but it's not that good because you just have the last 10 branches. It was practically not usable. Then they had branch trace store, but it would store a lot of data. because for every branch there is storing 25 bytes, where it came from, where it's going to go, and whether it was a predicted branch or not. It was very heavy penalty, sometimes 40 times. So you could use it just for one-shot debugging and not for continuous tracing. So now it's been improved as inter-processor trace, where you could do big complete control flow tracing. Basically, the idea is to record just the branches and then reduce the program flow later on by looking at the binaries and merging both of them. So you know where the branches were taken, where calls were taken. They have specific packets for that. For example, there is a packet stream boundary, which is like a heartbeat packet to tell that, okay, these are all the trace packets coming in. There's a paging information. Whenever there's a CR3 change, you just get this packet. There's TSC for timestamp, but that would be very expensive to keep on having. So they have some packets for timing called as mini timestamp counter, and or to use cycle accurate mode with C by C packets and then infer timing from that. For branches, which is the most important, is the taken or not taken packet. It's just 1 bit per branch, so it's very cheap. You just store 1 bit for the branch which was taken, and the target IP. If it was a call or if it was an indirect branch, then you need to know what is the target IP of that branch, so you would record that. And then you take all these big packets and you merge all of them and then decode them later on. So so I already talked about C by C packet for cycle accurate mode. You can actually get cycles, you can actually infer cycles for instructions from that. You can see how many instructions actually happened before each of the, in between each events that you get from hardware trace, how many instructions actually happened. Mini timestamp counter, I already told you, it's used to make the timing more granular, but at the same time the same cost of not using TSC all the time. So Intel PT is actually used by this way. This is a direct derivation from the slides by Andy Keene. He presented Intel PT, and actually that's how I got interested in hardware tracing. So this was in the last tracing summit. So you actually configure the PT using some MSRs which are already there, and then you run it. You just enable it on the CPU. The CPU starts throwing a lot of encoded packets, and there is some runtime data you save. Okay, wherever these binaries loaded at this time, what are the current libraries that are in the memory? So you can take all of this data from proc maps, and then you have all of it. And then there's this big software decoder, and some of this part is also open source. Basically the decoder library, and the PT implementation is now in the perf. So it's very open, and you can just do whatever you want with it. And then you have the binary of the application, and then you merge all of it and you get the whole reconstructed flow. So I already told you it's already in perf, and there's GD support now also. You can do accurate reverse debugging because now you have the now you have the flow data right in terms of actual instructions. So you can, if you reverse debug, it's more accurate now. You can try out clean simple PD. So how do these packets look? It's pretty complex. So this is directly from the auxiliary buffer of the perf. So these data is directly put in the auxiliary buffer. That's what ARM is also doing, by the way. And the decoded packets start from, like this is a timing packet. There are timestamp counters, timing alignment, and mini timestamp counter, as I was telling you. These are conditional branch packets, which I just mentioned before, taken or not taken. So you can see here, it's like these continuous branches were taken and then they were not taken. If you have so you can imagine if you have the binary data, you have your TSC before, and you know that the process starts from here, then you can, and you have the IP data by this indirect branches, so it may be a call, and after that there is a TNT, so you can know that in this function, the first branch you encountered was taken, the next was not taken, and then you can merge it all together and then decode the whole instruction flow. So basically you can get something which looks like ftrace directly from PD. The data is too huge, but you can actually decode and look at it. So this is a small example which I did where I disabled the RQs for some time and then re-enabled them again, and I could see the whole flow and how much time it happened between. This is the number of instructions that passed between this first import IOCTL and the second one. You can see it's a little bit more granular than ftrace because it doesn't even just tell you that it's calling this function, but it also tells you inside this function there was some branch at an offset of 38 and which called something else. So you see a little bit more granularity in that. How does it perform? So I just ran some tests on Intel VD to see if it's really very expensive to work. There were some examples which I did. I mean, but basically, mostly what I observed is that the overhead is basically because of the memory, because it's too much data coming right in the memory. So if you have your application which has a profile with very low frequency of branches, then you will have very less data. Is this question? Okay. So you will have very less data. But you may have huge data if you have, for example, something which is calling again and again, as you can observe here. So the first thing, there was a tail factorial. I just showed you a small benchmark, which just kept on calling, which just kept on making tails calls and just, calling it again and again. So what you will see is actually calls. And each of the call, as I told you, it's a indirect branch, so it's an indirect control flow. So you need to record the target IP. So for that you need the whole 64 bytes. So your data at this point increases so much. And we could see that the bandwidth was also very high. I mean, it was like 400, 500 Mbps something here. And so lots of TIP packets would be generated here. And as you reduce your complexity of application in terms of branching, for example, here this is pretty interesting. There was some random matrix statistics which were being done. Some of these tests are taken from the Julia RAM benchmarks. So you will see that the overhead was very less, and usually in all the applications which I found, it was 2% to 3% overhead which was happening. And for applications which were completely not having any branches, for example, here they are using Intel's index instructions for doing matrix multiplication, so they would have almost no overhead. So it really depends. This is if you do the same test but with the V8 engine. So you can even look at the JIT engine, how it's not that efficient. It's not using these new instructions. So anyways, this is another thing which I did, tracing the tracers themselves. What is the cost of actually using the tracers? So this is a small example of an nmap syscall, which is on the right, it's being called without the tracer. So you would just see, so the stack is, it's like a flame graph you can see, but just presented in terms of a round circle, and the stacks move from inside to the outside. So you would just see an entry syscall here, and then suddenly an mmap is being called. But if you had, here we had LPDNG enabled, so it goes through the, not the fast call path, but the longer path. So it took 173 nanoseconds more and 970 instructions. So you could see in a very granular fashion inside even your syscall. It's just an example. I mean, tracer is just an example. If something else happened inside the syscall, you would be able to even find that out. So, but this is normal for software tracers, and there are drawbacks on both sides. So, the timing granularity which we found is that you could vary it a lot. If you want a lot of timing packets, it would give you good granularity. Up to 14 nanoseconds, it could differentiate. But if you can even go higher granularity if you don't care about time and just about the flow. So we did another crazy stuff with PT, like analysis of the VM data, because PT is.
Can you go back in the previous slide?
Yeah.
So one more. One slide more. Can you go back?
Yeah.
So, as it is hardware tracing, I will expect not to have 22% of overhead.
Pardon?
As this is hardware tracing.
Yeah.
If you go to the architecture slide, where you see the picture of how this thing is, yeah, that one. No, the previous one was.
Yeah.
No, the previous architecture one, that's the process. Yeah, that one. So, when you see there, we are still using the same bus that the computer is using, right?
Yes.
Do you think that's exactly the same as the idea that the the first proposal of hardware tracing had. Because I think in the paper it was published, what they were doing was extracting from the bus, but afterwards they were using actually a different processor unit. I don't see if Intel PT has exactly the same architecture.
Okay, I studied with PT and I don't think PT has the same architecture. As I said, there are variations in this, so you could either use the memory bus or you could have a completely new, your own trace bus. I'll come to that. In ARM, they have their own trace bus. It's the different bus than the actual memory bus. But then they have ways to actually offload data from that bus to the main memory also. So because they probably realize that we can have more main memory and then we could use that to put traces. For example, in ARM, this hardware trace buffer is 4K, just 4K. And in main memory, you would have obviously overheads on your system. But then, as you can see with Intel PD, but then you can be more flexible. You don't need an external hardware to take out that data, or it really depends on the application. What kind of infrastructure you really want. Sometimes you may not even want hardware tracing at all.
But if I got you right, it's 20% they came from the memory transfer.
Yes.
So, and they are DMA supported by the hardware, or is it that you have to pick up the memory?
I think it's picked up. I will try. I'll try to see in detail what they are doing. But from what I understand, you basically allocate some memory, and then you give that memory, you give that address directly, you configure the MSR to use that. I'll confirm this.
Okay, you got an interrupt, you have to show it that
yes, and then
memory and copy it, so that takes place at 20% because it's pure DMA.
Yeah, pure DMA, obviously. So you could see that this overhead is because it's sharing that same memory.
Associated question, do you know if it's cached memory or non-cached memory? Because, if you could set it up in flash recorder mode and it stays, let's say, in L1 or L2 caches, if you have anyway associative caches, chances are you don't have to get the main memory. So that might be slightly better, but I don't know if it's cached or not.
The main trouble is with pulling the data.
Oh, microphone?
You can pass it on. So in both cases of Ecole PT and CoreSite, the data going through from the trace cell to the memory will be DMA'd per se. Right? So if you set it up in flash recorder, the only overhead you will get is the extra boundaries of the main interconnect. And it will, well, I'm not 100% sure about the intensity, but it would be entirely crazy to have any interaction with the cache at this moment, right? And this will give you a probably measurable but very, very minute overhead, the trace infrastructure itself. But the way it is being implemented with PER, well, the way you have to implement it when you want to have a self-hosted trace with full trace record is that you will get, well, pretty much an interrupt every now and then when you have to drain the buffer when it's full, right? You will have a huge buffer in DRAM, but it's still finite, so you will have to drain it, and that's where the larger overhead will come from. So, flash recorder, very little overhead. The full self-hosted trace with full trace record, measurable and potentially high overhead.
Okay, but one thing that I'm thinking about here, doing latency tracing, and I think you can put the embedded trace buffer on ARM in a ring buffer mode.
Yeah.
And if it's large enough, or if you don't have too much branches, you can just let it run in a ring buffer and collect afterwards when you finish with your trigger.
That's actually the way it's supposed to be used. That's the way I see hardware tracing to be used right now. Because it would be unimaginable to have like GBs of data for a few seconds and then trying to analyze it. A good way is to just have it in like flight recorder mode, the way LTDNG has it, and keep on recording. And when we detect some abnormalities, we just take this previous snapshot and then directly analyze it. So yeah. Okay, so I'll continue. So we did something very crazy because Intel PT also puts out VNCS packets, which is VM-related packets, which is the value of the VNCS register, and we could analyze inside of the VM directly from PT itself. So it was like a crazy idea which we had, and we actually did that with Trace Compass, and we could see that this is like a resource view of 3 CPUs, 4 CPUs, and we could see one process being jumping between the 4 CPUs. Actually, these all 4 CPUs were pinned on one physical CPU, so just so that we could see these jumps being happening. So the next view, for example, is a process view where there are 3 different processes, and they were also pinned on a single CPU, and they were doing something in round-robin fashion, so we could visualize them. So you could get all of this information without even touching the VM or without even doing software tracing on the host. You could see this minimal information directly from hardware traces. So it's not mature, but there's potential. That's what we wanted to show. So let's come to ARM core side. I didn't do like in-depth experiments on it, but I at least basically did some experiments where I could get the traces and start some decoding. So ARM used to have like because they actually had a very good infrastructure on hardware tracing from already from before with ETM v1, v3, and then they have moved towards ETM v4, which is a very mature implementation, and it looks very similar to PT. For example, you would have same kind of elements. I'll just show you in the next slide. So you would have an processing element, for example, P0. So for different ARMs, for example, A family, ARM A, and then M, and then R family. So for A family, there's only instruction tracing, and for M and R family, they have data plus instruction both tracing. And the elements are like P1 and P2 are data elements, and P0 is instruction elements. So we care only about P0 now because that would be a fair comparison between you there. And you can see the atomic elements are actually taken, not taken, which is the branch was enabled or not enabled. And Q elements are like the CYC packet, the cycle count. Then there is conditional element, conditional branch if it was a conditional branch. Result element, I don't exactly remember what it was. And then other lot of stuff like branch mispredict and everything. So it looks very much like Intel PT the way it has been. But as I've just been reminded, so as you see here, so the processing element can send the data to the trace router, and which can then send the data to the system bus and then to the system RAM, or it can send the data to a trace router or a trace FIFO. So these configurations are mandated by, not mandated as in they have been suggested by the core side infrastructure, and they can be implemented on silicon the way they should, the way the vendors want them to be. So they can configure the components of their tracing. So you can have it directly go on a trace FIFO with directly interfaces to a trace port interface unit, which takes it to an external hardware through JTAG or whatever we use. So, but what we are probably interested, or what I'm probably interested in to do like in-memory tracing, hardware tracing. So that looks pretty interesting. So, so I already told about that. Decoding is these days with OpenCSD. It's a library which is open source now by ARM, and Nano has been working on it for quite some time. Matthew also mentioned it yesterday. And you could set filters on it. It's the same with PT. In Intel PT also, you could set filters on directly on functions. I want to trace between this function and that function. So that's one way to reduce the whole overhead itself. So you know that I want to have a hardware trace between this function and that function. We just configure the MSRs to only trace that part, and you could save a lot of bandwidth this way. I mean, ARM also has a very similar infrastructure. So the OpenCSD's decoder and has also been merged with perf, so you could actually control the trace right now with perf, the way you do with Intel PT also. I should have those slides, but that information is very readily available. You just need to look at the kernel documentation, and they have Intel how to use it. So this is, for example, the view of SOC in terms of trace units by ARM. So they have a dedicated trace bus, and they have something called as funnel, where they could take trace from different sources. So here is EPM, for example, and then there's a trace replicator. If you want to save it to the buffer or to put it to the trace unit, you can do data to the data trace to one way and the instruction trace to another way. You could configure it like that. There is embedded trace router and then FIFO, which embedded trace FIFO. These elements connect to probably system RAM. So it's really configurable this way. Forget about this DS5. We just care about the kernel. So the kernel views it it's something like that, where everything is exposed. All of these elements, funnel, the replicator, and then the embedded trace routers and FIFO, they're exposed to device trees, which the co-site driver can use. So I think 3 boards are now completely supported. And I was trying out with one board. I could not get the EDR working on it, but that's another story. And then you would configure the sink and the source. You would tell that, okay, I want this ETM and I want this ETR as my source. So you could do that. So I did a small experiment with OpenCSD and setting it up like this, and I could get the trace. So that's mostly my experiments with ARM hardware tracing. Now we go a bit deeper to Baremetal tracing, where we are gonna explore what happens when you have a system which has different kind of cores. So chip boundary used to be like that. There was one CPU and you will work with that, and the life was so easy at that time. Then you started having multiple CPUs, and there were some complexities in terms of getting data out from there. But now, this is what's happening these days. We have GPU on the same chip, we have DSPs, and we have an FPGA on the same chip, and you'll have a lot of data coming and going from each of these. There would be a lot of communication happening between them. Then how would the tracing world evolve with that? So Tom worked on it a bit, and he used TI's Keystone as an example, which has 8 C66 core PAN DSPs and 4 Cortex A15s. So what would happen in such systems? How would we approach tracing? What happens if we have multiple cores? So how are we going to synchronize traces coming from the main core and the other core? So these would be examples that we have. So there's a solution. There's something called as BareCTF. It has been developed by Philip in Vicious, and we can use trace numbers to visualize the traces. So we did both of these things to analyze Baremetal tracing. So this is from LPH's blog. You can just go and look at it. So that's a good post. You should check it out. So that's what's actually happening with BareCTF. You have the BareCTF program, which takes the configuration, which is platform dependent, in a binary file. You read that configuration, and it generates you 3 files: BareCTF.c, H, and the bit field. And then you can use these trace points with your application, and then when you run the application, it starts generating the traces. So this is similar to this. You initialize your traces, you initialize the function, you run it. So the problem, not the problem, but the complexity here lies in implementing your platform. So you have your dedicated platform, you have to implement these functions with these APIs. It's pretty standard. Once you have a platform ready, it's done. Now you can move on to another hardware. So I think currently 3 or 4 platforms are already there. Parallel is working, this TLA is working, and we are able to get hardware traces from that. You can get this API later on. So our workflow for our small experiment was that we had a master, and the master would run, and it would generate code, it would generate traces, and the traces would go to LTNG. So this is a normal run. But now we have slaves which are DSP cores, and we want to get data from them. So you would have a BareCTF consumer here, and the BareCTF is generating traces through the cores, and they will get then merged. How they are going to get merged, you are going to see that. So you can synchronize these traces with a master request. The slave, okay, here is, you have to prepare a packet now, the data is saved in CTF, and then it goes back to the master, and then you can do it. So So here's a small example we did of image filtering, and we used message queue APIs with that DSP, and it was running some functions. And initially, if the trace is not synchronized, you will not see anything. It's just like black box in terms of DSP. But when you synchronize both the traces from the ARM hardware and from the DSP, you will have a view like this. So here you can see, that's the interesting part. This is the communication happening between the ARM code and the DSP's code. So you can see here this part, I just magnified it, and you can see the first DSP was processing the image, and then you could see all the other DSPs. And if you see this part, you could see the message queue being requesting between the for memory allocation between the ARMs and the first DSP, which allocates memory for that. And then we just introduced a small workload to show you the latency here. So this small dummy workload is pushing the processing of RGB on the other two DSPs back. So you can have something else which is running here, and you will see your latency is being high. So that's mostly what I have, and I mean, the future looks pretty good, and everything is getting integrated. Probably in terms of hardware tracing, we need to have standardization. In terms of heterogeneous tracing and Baremetal tracing, we need to have standards which mix all of these things together. Here are the references. I won't take much time. Thanks to Vishwas, thanks to Ecole Montreal, Datt Lab, and Datt for having me here.
Okay, any questions? And while we have questions, you can try to set up the laptop beforehand. Any questions related to hardware, Chris?
When can we get these music examples?
Very soon.
Most of us want to serve this.
No questions? Yes, one question.
Well, one of the key problems is that you have different cores, and core DSP and stuff. How do you get a common time step? And what is the let's say, the jitter or the accuracy of getting a clock somewhere out in the SoC?
Yes, this is something which is a problem. I mean, synchronizing the traces, but there are ways to synchronize traces which are having different clock sources. So you could estimate that difference, and you could actually correlate the different clocks. So we tried that, and the views which are being showed were with relations in clocks between the ARM and the DSPs.
Actually, I think this is a lack of SoC architecture.
Yeah.
Let's say, common accurate clock which can be accessed on all cores.
Yes, it really depends on hardware. That's why BareCTF, which I see is being designed as very modular. If you have another hardware, you could just describe it yourself. Even the clock sources, in BareCTF you can describe the clock sources. And then that makes it a bit more modular. And it's very open. For example, for synchronization, as you're seeing, for TI it's very easy. There's a message API, message queue API, which can talk between the ARM cores and DSP cores. But on parallel, you need to implement it yourself in shared memory. So it's too much architecture dependent, I would say.
But I believe in CTF there is a way to describe those custom clock or the.
So you can describe those plots in CTF, however, you basically, the missing thing is the correlation point. So you describe each of the clock, their frequency and everything, but then at some point there will need to be either some message being exchanged or some user interaction, which is going to basically align the traces. So that's kind of the missing link.
What I would suggest, I mean, to hammer on that is if you have some testing routine running on the different cores and see how much clock jitter you will potentially get, that gives you a kind of idea how much shifting of the different traces you have to take into account when you look at the traces. So that could be maybe the clock probing on the different cores and correlate them and see how much jitter you will get under a test condition So you can make this information and you can use it in the trace.
I mean, we'll take the rest of that discussion offline because we're a bit short on time for lunch and everything, so we'll skip to the next speaker. But yeah, I mean, we can describe the precision of the clocks in the CTF clock and the data. So, I mean, at design time, that can be assessed. Thank you.
Okay.
Thank you.